In this video, I introduce a decision transformer reinforcement learning via sequence modeling. A Markov decision process is described by a table with the states sampled from S, actions sampled from A, transition dynamics P, and a real-world function R. The goal of reinforcement learning is to learn a policy to maximize the expected return E, where T is the number of steps in a trajectory tau. Transformer with causal attention is used to find the optimal policy. The self-attention uses the query QI, key, KI, value Vi obtained from the embeddings X to produce attention distribution Z, as shown here and explained in this figure. This input X. Causal attention use Q and key to generate this attention mask. This attention mask uses as a weight on this value V to generate the attention Z. And then we use feed-forward layers to generate attention distribution. That is used as the input to the next attention block. The autoregressive process is modeled by using causal self-attention, namely the current state and action can only depend on the previous states and actions. Decision transformer models trajectories autoregressively through causal attention, which uses the transformer to model reinforcement learning as a sequence problem. States, actions, and returns along a training trajectory are first embedded into a latent space, and the embeddings are fed into transformer to predict the actions autoregressively using the causal attention mask described above. Since reinforcement learning models the expected real-world along trajectory by estimating future desired return, decision transformer predicts a sequence of actions by modeling a return to goal. A trajectory tau is represented as here and explained in this figure. This is a return to goal. Given state S, the model predict action A, and then we use S and A to recalculate the return to goal. The last key time steps in a trajectory with 3 times key tokens are fed into decision transformer. A linear layer for each modality projects inputs into the embedding space, followed by a layer normalization. The decision transformer uses the embeddings to predict future action tokens. A mini batch of sequence length key is sampled from the training dataset. Decision transformer is trained to predict the action AT for each state token ST with cross entropy loss for discrete actions, or the mean squared error for continuous states. The losses for each time step are averaged, as shown here. This return to goal, given as the model predict action A. And then we use state and action to recalculate the return to goal step by step. The goal is to find the maximum optimal policy with the maximum return. During evaluation, decision transformer specifies a target return based on the desired performance as well as the environment starting state to initialize generation. After executing the generated action, decision transformer decrements the target return by the achieved reward and obtains the next state. This process of generating actions is repeated and then obtains the next return to goal and state until episode termination. For more details, please check with these references. Thank you. Bye.